I would like to ask the esteemed participant to switch off their microphones, except for the speakers. And we start with the intervention of the rector of the Russian University of Transport, Mr. Alexander Klimov. Please take your floor. Mr. Klimov, please.
Dear Sergei Hua, dear Heikki Degim, dear speakers and participants of the forum from many countries. On behalf of the organizing committee and on behalf of Russian University of Transport, I am glad to greet you at the first International High-Level Forum on Smart and Autonomous Ships. Today we are witnessing an amazing progress in different areas of transport. Just 10 years ago, unmanned cars, aircrafts, and ships were the subject of scientific research only. And today we see how they come to the real practice of industries. And this is the new reality for the maritime industry. Today we will see real practical cases of its implementation in different countries, in China, Japan, Finland, France, Korea, Norway, and Russia. Because the maritime transport is a global industry and the autonomous navigation implementation requires global effort. Universities play significant role in such developments in every country, and our mission of our universities is to establish strong international cooperation in autonomous navigation development. We have to provide open platform for ideas and experience sharing for academic and research teams for training and talent development. Together we can build the new, safe, and sustainable future. To do this, just a few minutes ago, we discussed with colleagues from several universities to create a joint international lab on smart and autonomous ships. But we will be very glad to see all universities around the world working in autonomous navigation and smart ships technologies and call all universities to join us. Also, we believe that the International Maritime Organization will take leadership in guiding and focusing efforts of our international joint lab. I call distinguished delegates of our forum for open discussion and free sharing of knowledge and experience, and wish successful and fruitful conference today and tomorrow. Thank you.
Thank you very much, Mr. Klimov. And it's a special honor for me to give floor to Mr. Sergei Gukua, Vice Rector and Chairman of the ICNAM. And please, the floor is yours.
好，这个尊敬的
Thank you very much, the respected Mr. Heikki Degim, President Klimov, ladies and gentlemen, dear experts, good morning, good afternoon, or good evening. I am very happy today to witness the opening of the first international high-level forum on smart and autonomous navigation technology of ships. On behalf of the ICNAM, as well as Harbin Engineering University, I would like to extend our congratulations to the successful opening of this meeting. Also, I want to thank all of our members of the organizing committee, including Marinette Center and Russian University of Transport, Wuhan University of Technology, etc. They have contributed amazingly to this forum. I'm sure we'll have a successful session. With the AI, computer science, and information technologies developing rapidly, unmanned ships and their autonomous navigation are becoming more and more mature technologies in the world. So today we have invited the top-notch universities and research institutes and companies in this field. We will discuss together how to promote the autonomous navigation technology, its development, and also to establish or build this partnership among different players, so that we can see the translation of such technology into application as soon as possible. This is a great forum. ICNAME is going to continue to build the platform for the promotion of this technology. I am pretty sure that in the near future, unmanned ships will be traveling across the oceans. And finally, I would like to wish this forum a full success. Thank you.
Thank you very much, Mr. the Chairman. And now I am very glad to give the floor to Ms. Heike Degim, Director of the Maritime Safety Division of the International Maritime Organization. The floor is yours, please.
Good morning, distinguished participants, ladies and gentlemen. Thank you very much for inviting IMO to participate in this high-level forum. It is a pleasure to be here this morning. IMO's Maritime Safety Committee has been discussing the matter of regulating maritime autonomous surface ships, or MAS as they are now universally known, since 2017, when the 98th session of the committee took place. At that session, the committee considered a joint submission by Denmark, Estonia, Finland, Japan, the Netherlands, Norway, the Republic of Korea, the United Kingdom, and the United States, proposing to undertake a regulatory scoping exercise to determine how the safe, secure, and environmentally sound operation of MAS might be introduced in IMO instruments. Since then, the work has been progressing steadily. MSC 99 in May 2018 defined the aim and objective of the regulatory scoping exercise, the preliminary definition of MAS, and the list of mandatory instruments to be considered. MSC 100 in December 2018 approved the framework for the exercise, including the work procedures, and a new GESIS module to facilitate the exercise was developed. And MSC 101 in 2019 continued the scoping exercise and also approved the interim guidelines for MAS trials. Following MSC 101, we had an intersessional working group on MAS, which met in September 2019 and progressed the work even further. At the same time, the legal and facilitation committees of IMO also commenced a regulatory scoping exercise of the instruments under their purview, while the Marine Environment Protection Committee decided, taking into account its heavy workload regarding greenhouse gas emissions from shipping, to consider MAS in the future when significant progress would have been made on the matter by the MSC and the legal and file committees. But with the COVID-19 outbreak in early 2020, we hit the buffers. The program of meetings at IMO was severely disrupted since physical meetings were no longer possible, and it took us a while to adapt to the new way of working through remote meetings. However, we have now perfected the remote modus of meetings, and most of the regular IMO meetings of its committees and subcommittees have taken place as expected, albeit with much reduced agendas due to the reduced time frame of these meetings. Because of these limitations, MSC 102 in November 2021 deferred the consideration of MAS to MSC 103. MSC 103 which took place in May of this year, finalized the regulatory scoping exercise, and the outcome was distributed by means of an MSc circular, that's MSc Circular 1640. The objective of the scoping exercise was to assess the degree to which the existing regulatory framework may be affected by mass operations and to identify items for further discussion in the future. Finalizing the exercise enabled member states to consider the next steps of the committee for substantial work on MAS, such as the further development of definitions, for instance, MAS, remote operator, remote center, and so on, amending existing instruments and or developing a new separate instrument, addressing MAS operations in accordance with the results of the scoping exercise, and also looking at updating the interim guidelines for MAS trials. We also need to take into account the need for harmonization of the work on MAS between the IMO committees, in particular concerning terminology and definitions. For this, a joint working group of the committees may be needed at some time in the future. There are many concerns with regard to the effect of the introduction of autonomous ships on the safety of navigation. One of the main issues for discussion is the interaction between conventional ships and autonomous ships. In this context, it has been recognized that the Collision Regulations Convention is one of the most critical instruments. Views have been expressed that some amendments to COLREG are required in order to accommodate the use of future autonomous shipping without seafarers on board. However, there is general agreement that COLREG in its current form should still be the reference point and its current content should be retained as much as possible. The STCW Convention has also been identified as a critical instrument, since the introduction of MAS without seafarers on board would transfer the role of officers on board to the remote operator or another entity for whom training, certification, and watchkeeping requirements should be established. IMO member states took all these aspects into account. At MSc 104, which took place last month, the committee considered submissions from a number of member states, including the Russian Federation, with proposals on how to proceed with the work on MAS. As a result of the discussion, the committee agreed to develop a goal-based instrument for MAS and included a new item on development of a goal-based instrument for maritime autonomous surface ships with the target completion year of 2025 in the agenda for MSc 105, which will meet in April 2022. The committee also agreed that the first step in the work on the new output should be the finalization of a roadmap for the work to be carried out. Consequently, it requested the chair of the committee, together with the Secretariat and in consultation with the submitters of the proposals, to prepare a draft roadmap, including scope, steps, and timelines, as well as the coordination of work with other IMO bodies for detailed consideration by a working group at MSc 105, with a view to approval by the committee. In concluding, let me wish you all success for this high-level forum, and I very much hope that the results of your considerations will find their way to IMO to support the work on developing international regulations for MAS. Thank you very much.
Thank you very much. First of all, I would like to express the gratitude of all the participants to you for finding time to participate. It also marks the importance of that the International Maritime Organization pays to the forum, to the session. And secondly, I think that in your very extensive, very condensed presentation of the most core ideas of the IMO, you have marked the milestones for many aspects of the work in the field of autonomous ships, the relationship with the safety issues, relations with coordination and relations with other department activities, and so on. I think that your speech was very inspiring for the participants of the forum, and we sincerely thank you for your speech, for your participation. Thank you very much. And now I would like to give floor to Mr. Yang Xinping, academician of the Chinese Academy of Engineering and professor of the Wuhan University of Technology. The floor is yours, please. Sorry, there is no sound.
So, Professor Yan, can you open the speaker? We can't hear.
Hello, could you hear me? It's okay?
Yes, thank you. Now we hear.
Okay, sir.
I'm very sorry, now it's no sound yet. Again, no sound, sorry.
Sorry, I'm sorry. It's okay?
Now it's okay.
Okay, so. It's okay. Thank you. I'm Qingming Yan from Wuhan University. And my presentation today, the title is Development of Maritime Autonomous Surface Ship in China. And the chairman of this first international forum, Professor Guihua Xie, invited me to give a talk. I think it's very hard for me to, because in China, there are so many organizations as the institute and also the university. They have done a lot of the research and on this area. So I want to collect more information to give the general description about the water mass in China has been developed. In my presentation, sorry, I think the PPT is also cannot go on. What's the problem? Oh yeah, there are 5 parts in this presentation. The first is introduction, what's the background, and how can we make the activity in this area. And then I will focus on the 3 activities. The first is how can we develop the master rule and the standard. The second is about the technology. Then we will discuss the platform for leverage and test the smart ship. The last part is about the how what we have done in the future. As we know, maritime autonomous surface ship is defined as a ship which can be very degree, can operate independently of human interaction, integrate the cutting-edge technology in artificial intelligence, information and the communication sensors and the control and the system. MES is believed to be the safer, greener, and more efficient than traditional ship, which has become the high technology in the shipyard. MES is the trade and the feature of the shipping industry as we know. Mostly focus on the three directions. One is the digitalization. The second is the connection, then the automation. We also know the MES technology will improve the performance of the ships and then make the ship more safety, in economy, and in eco-friendly and more efficiently. So this is very important for the MES. Since 2015, China closely followed the cutting-edge technology of MES and has successfully issued the action plans and the guidelines for promoting the development of MES in China. Chinese researchers and engineers mainly focus on the three key aspects of the MES. The first one is how can we develop the rule and the standard for the MES. The second one is we developed a lot of different intelligent systems used in the ship, and they have the very useful in the really ship. The third part is how can we develop the test the ship. That means we use the ship to test the different function of the intelligent system. Also, we establish the test bed. Okay, next part about the MES rule and stance. We know in the world up to now, there are several different kinds of the organization publish the MES standard. Take an example, IMO focus on the technical regulations. For the Lloyd's Register, most focus on the analyze the relationship between the people and the ships. And for the Rolls-Royce, they may focus on the part implementation. So in the different organization have a different angle, but they also make the smart ship is a different level. We also do this kind of work in China. The Ministry of Industry and Information Technology has issued the guidelines for the construction of standard system for intelligent ship. In this way, to improve the development of MES and the technical standard system. In this system, including 7 different parts. The first one is the foundation. The second is the key technology. Then the design of MES. Also the ship side intelligent system, and the test and the validation, and also the shore set servers. And the last one is the operational management. In China, in order to meet the demand of MES, CCS has issued the first rule for the intelligent ship in 2015 and updated the rule in 2018. The rule has addressed the function and the requirements of various intelligent systems and the equipment used in the ship. There are different levels for the intelligent ship. Meanwhile, CCS also issued the guideline for autonomous cargo transport vessel. also the inspection guidelines for unmanned surface vehicle and other detailed guidelines, which greatly improve the space in China. And this different law make the different solution for the different type of the vessel and the vehicle. CCS law also including the 6 class notation. The different notation have the different function. For example, take an example. The N means the smart navigation function notation, and H means the smart hull function notation. And the third part, we will talk about the MES technology developed in China. There are 80 different kinds of the technology has been developed in China. The first is the intelligent navigation system. Then this system can enhance the perception of different level of mass based on the big data, VR and AR techniques, machine vision techniques has been developed, also tested, and also applied in different type of ship, including the ocean and the inland ships. Also, we have developed the intelligent CNC system that support the mass dock, forward pass, and provision collusion without the human interfaces has been tested, and also in the small simulation experiment environment, and also the really ship. The second one is intelligent machine maintenance. We developed this kind of the system which can collect the operational data from the massive sensor on board, diagnose the state of the machinery, and managing the maintenance schedule and develop for the ships. That means we use the different transducer, for example, vibration sensor, also the oil debris analysis, and so on. We also developed the intelligent integration and the remote diagnosis cloud platform. This platform can be share the knowledge and offer service for remote monitoring, operation, and maintaining the marine equipment. The third one is about the intelligent energy efficiency management system. This is very important for the ships. It's developed to collect the oil origin consumption data, analyze the state of the operation, and optimize the operation with respect to the energy efficiency. The first one is the intelligent liquid cargo management system, which provide guidelines for the loading and unloading, and wash the carbon, reduce the difficulty of the operations, and also improve the cargo management on the shore. The fourth one is about the intelligent integrated platform. And this platform on the board is developed, which collect the data from the ship and to the ship with the protection. The platform is established to improve the information share across different equipment within and behind the ship. The sixth is about the mass activity. So about how can we design mass? This is a very important area. We also actually in this area also actually marvelous attention in China. The mass with intelligent notation are designed by Chinese Institute. Take an example, the VLCC, second generation VLCC. In this ship, they have the 5 different functions of the intelligent system. For example, assisting the corrosion prevention, energy efficiency management, and also condition test the maintenance and so on. The second case is as a COSCO shipping loss 13,500 TEU container ship. They have 4 intelligent system and in this ship. For example, the intelligent integrated platform, intelligent machinery system, intelligent energy efficiency management system, also the intelligent navigation system. The 7th activity research for the MES is about the navigation brain system developed by the Wuhan University of Technology. This system is a software within a decision-making system using artificial intelligence and to process rule, regulations, and experience. The NBS offer a theoretic and technological foundation for combined AI and the ships. We also use this system to develop the some system used in the Nanjing Banqiao ferry. This system support the perception of the official on watch and their decision in poor visibility condition, such as fog days and night times Islam. We also use this system applied to Putuoshan ferry in Ningbo City, which contain a shore-side route management system and a ship-side navigation assistance system, which supports the protection of ferry manager and officers on watch in poor visibility condition. The last intelligent technology for the MES is about the MES test, and also we use this technology in the conformed water, especially in the inland region. 244 TEU container ships are designed that can perform navigation assistance, remote control, and conditional autonomous navigation in waterway network. The further part is about the test platform. Supported by the Minister of Industry and Information Technology of China, experimental Ro-Ro ship is designed and built in Harbin Engineering University for testing intelligent protection system. There are different functions, including the 360 perception based on sound, night, and electronic singular, and so on. Also the rebuilding and of situation, also sensor, including the radar and the camera and the lean also, so on. The second one is Haitun 1 is a 25-meter experimental ship. It's developed for the testing K-MES technology, which could perform remote control, autonomous navigation, also autonomous dark Islam. The Harbin University also developed the simulation platform for the intelligent ship, especially for the MES. We also developed the test bed for the autonomous ship in Guangdong, Zhuhai City of Guangdong province. It's a service from 2018. This test bed is around 770 square kilometers. The test bed is being undertaken by the Zhuhai government, China Classification Society, also Wuhan University, and the Zhuhai Yunzhou Intelligent Technology Company. Next is why I wanted to talk about how we will do in the future for the math. And this is there are 5 areas. The first one is the design of green intelligent ship. Ship design is a basic stage of developing a green intelligent ship, which guarantees the goal of green and intelligent. The following 3 aspects should be focused. The first is the benchmarks of the green intelligent. The second is the new methodology of ship design, the developing green intelligent ship forms. The third is about a test method for the green intelligent ship form. The second thinking should be focused on is autonomous navigation of a green intelligent ship. Intelligent navigation has a focus stage, including enhanced navigation, assistant navigation, remote navigation, and also the autonomous navigation. I think it's a long way for us should be to go. So also 3 research area should be pay more attention. The first is remote control based on the ship-shore cooperation and the human-machine cooperation. The second is autonomous navigation and formation of heterogeneous ships. The third is the virtual really interaction test platform for autonomous navigation. The third research direction is about the green energy efficiency control of intelligent ship equipment. Considering the environmental concern in the inland and offshore region and the safety concern in the complex waters, it is necessary to study the green equipment and control technology on board. Thus, the research should be including, but not limited to, 1, general framework of green and emergence energy efficiency control equipment on board. The second, the configuration solution for the green power system on board. Also, the continuing-based maintenance, the integrative control, and the comprehensive control for the green intelligent ship equipment. The fourth research direction is about the safety of green intelligent ship. Navigation safety is one of the important things. Also, the challenge of the application of intelligent ship. Considering the development of existing technology, the research on the safety of green intelligent ship, including the following 3 aspects. The one is the safe navigation technology for green intelligent ship. The second is a risk assessment for cyber security of green intelligent ship. Also, the risk assessment for new energies of green intelligent ship. The last one, the last important research area is the validation and the stance of green intelligent ship. This is key for the design, key technology for the design, building, operation, the maintenance, the green intelligent ship in the future, which is fundamental for the popularization of the green intelligent ship. Also have the three research areas should be pay more attention. The one is the key technology for test and the validation green intelligent ship. The second is the standard formulation of green intelligent ship. The last one is maintenance of convention on green intelligent ship. In the last, I want to give thanks to all of you, especially for our Chinese colleague. In order to prepare this presentation, so many professors and senior engineering working in the different organizations and university in China provide a lot of the information and ask me and hope me to display and their work for all of you. So I want to give my thanks to all of them. Thank you again.
Thank you very much, esteemed professor. Your report was of greatest interest, and I think that it's because of its comprehensive and highly systemic character. I think that we will not be able to find any aspect which was not covered extensively in your report. So it helps us to have a very systemic vision of the topic that you covered. Thank you very much again. And now I would thank you. And now I would like to give floor to Professor Janne Lahtinen, representing the Satakunta University of Applied Sciences in Finland. Please, the floor is yours, Professor.
Many thanks all. Let me introduce myself. Yes, I am Janne Lahtinen, a professor in the Satakunta University of Applied Sciences, working there as a senior lecturer and marine autonomous researcher. Allow me to share my screen. Start with that. Can you please confirm me that at this time you can see the slideshow presentation?
Yes, it's good.
Thank you very much. So, having said that, I represent Satakunta University of Applied Sciences. First, a couple of words of who we are and what do we do. We are a higher level education provider in Finland with 425 personnel, almost 7,000 students, more than 30 different degree programs with bachelor's, master's, and open UAS programs and educational services, courses, and seminars and such. Engaged also to a lot of domestic and multinational projects with the annual project funding hovering between 10 and 20 million euros annually. So it is a very considerable area of activity for Satakunta University of Applied Sciences. We are 4 campuses here in Finland. Presumably everybody knows where Finland is. So here in the windy west coast of Finland. We are in 4 different locations in the cities of Pori, Rauma, Kankaanpää, and Huittinen, where I myself am at the moment sitting in Rauma. In SAMK, our values and mission are making results together. We firmly believe that there is very little that we can achieve without broad collaboration with the co-experts and good colleagues, both domestically and internationally. We encourage curiosity and inspire responsibility in everything that we do. And goes without saying that as everyone, we also want to exceed all expectations set to us. Our mission, basic mission, is to provide experts serving industry needs. And this is a very interesting area in our thoughts due to the fact that the industry needs are migrating with development related to digitalization and automation in all traffic forms, and not least to the maritime. So it is a very challenging mission. And apart from this, our basic goal is that all our students are employed. So we wish to be on the edge of understanding what the industry needs really are, so that we are able every day providing the training for the students for them to best serve the industry that is surrounding us. Now, we have master's and bachelor's degree programs in English. This is a shortened list, which only includes the ones that are engaged to the maritime industry: maritime management, sea captain, marine engineer, artificial intelligence, logistics and maritime logistics, international business and business management, and also entrepreneurship are the programs that we are doing. From the research side of things, we have a research center for maritime logistics, aiming to support the growth and competitiveness of the enterprises in maritime technology and logistics in the municipality of Satakunta, and also domestically in a wider perspective. We create research infrastructure, high quality research and international product development available for the enterprises. So this is the part of the work that keeps us tightly engaged with the industry that surrounds us in maritime domain. Contact information related to SAMK, I'm happy to maintain in your disposal should you have any questions related to what we do. We have a very limited amount of time, and we are a university of nearly 7,000 students, so it's not much time to actually tell more in depth of what we are on about. But I am happy to continue the discussion later on, so please do not hesitate to contact me once this presentation is finished. This was about SAMK. This was about the Satakunta University of Applied Sciences. And if you allow me, I will tell you a few words about practical projects that we have been engaged to and that we have been leading related to the development of maritime autonomous systems. Maritime autonomous surface ships and the research that we do. I have split the roadmap in 3 areas for the sake of this presentation, talking about the target, tools, and the results. Where environmentally and financially sustainable autonomous marine traffic solutions are the target, and the tools to get there are the research gravity on solutions that add value to all fairway users and logistics chain stakeholders. We will look at these parts more closely in a wee while. Results, practical solutions, streamlining current operations and contributing to higher levels of autonomy in the future. So the target is to enhance safety, sustainability and efficiency in maritime operations. It goes without saying that the first and foremost thing in our mind when we are introducing these changes into the maritime domain is the safety. We need to be able to do things at least as safely, if not more safely than what we are doing today. We also need sustainability to create solutions that are both environmentally and financially sustainable. It is a known fact that we, the humankind, we've been in the moon, but we're not going to the moon at the moment. There are no projects aiming to the moon due to the fact that basically the commercial attraction is no longer there. Whomever is there is not the first anymore. Whomever is there, it's very unlikely to find out so many new things about it anymore. It's basically all about the financial attraction and the sustainability. The tools. Collaborative international autonomous research projects with focus in summoning international research work and technology providers to facilitate development of maritime autonomous ecosystem. We put a lot of value in the international research and collaboration with multinational co-workers and colleagues due to the fact that we understand that to create sustainable solutions, we have to understand solutions that are also upscalable. When we do the research domestically in Finland, yes, we have ice, yes, we have summertime, we have the hours of darkness, we have the hours of daylight, and everything in between. We have very congested waters and big archipelagic areas, which are very demanding for the navigation, in particular in the winter time. But it doesn't change the fact that in order to create solutions that are globally upscalable, we need to challenge these novel operations and ways of doing things in various different environments. And in the ideal world, this happens somewhere else also than in Finland. And this is just one of the reasons why we see the collaboration in traffic domain and in particular in maritime as a very important factor. And the results that we wish to see is collaborative international research community that enables financially sustainable testing and safe commissioning of novel maritime autonomous solutions. Low threshold testing and testing that can be done without extensive investments in very expensive equipment and using the time of ships and commercial vessels is probably not the most sustainable solution, at least not financially. Therefore, through the collaborative international research, we could be part and we could participate in creating environments where a low threshold, safe and financially and environmentally sustainable testing of novel maritime solutions can be enabled. So, a couple of words about what have we been doing so far. Paving the road. When we look at this picture, at least those of us that are engaged into maritime domain recognize probably this picture from thousands, if not tens of thousands of bridges of maritime commercial vessels globally. It's an autopilot user interface. It's not exactly a new one, but it's not my age either, but somewhere in between. And the road to enhance safety, sustainability and efficiency in maritime operations, we believe, is paved with simple systems that work. Like what we're looking at over there, the autopilot. It already makes decisions that are only partially depending on the human involvement. We build on things that we know today. While doing so, we believe that we should remember that the intelligent solutions, they are not actually the goal, but they are the tools to achieve the goals. Technology is not the aim point. Technology is the tool to get to the aim point. This is our thinking. Now, through the projects Aava and Swan, of which you can find more details from the link below, an autonomous ferry was already established in 2018. This work now progresses through understanding the demands for the safety and sustainability of future maritime operations. Smart fairways. Traditionally, we all have, if we can speak of traditional approach when we are talking about autonomous solutions, but we are used to engage the autonomous development into the vehicles. All the new gadgets, the technology, the improvements, the enhancements, they all lie in the vehicle. They are in the car. They were in the autonomous ferry with the projects AVA and SWAN and so forth. So the development has much materialized as technically advanced cars and ships saturated with technology. It's generally known, however, that in traffic you can do absolutely everything right. You can wear the seatbelt, you don't SMS, you are focused, you're alert, you have rested, you follow the regulations, and you can still end up in harm's way. And this is due to the fact that all maritime and traffic situations are actually contextual to what happens around you. It's not only about ourselves. We can do everything right and still things can go bad. So we believe that to increase safety, we should focus to solutions that contribute to the safety of all fairway users. We acknowledge the fact that through developing the safety of all fairway users, we are both directly and indirectly enhancing also the safety of our own operations due to the fact that people and the other fairway users in maritime domain, that is, around us have a sufficient situational awareness and safe mode of navigation. So the combining factor for all fairway users is obviously the fairway. And the smart fairway could enable other novel services, such as, for example, remote pilotage. Remote pilotage is not much more pure mass as is the intelligent fairway or the smart fairway infrastructures, but they are paving the road towards more developed solutions. So remote pilotage, the pilot is moved from the bridge to a control center ashore, and a conventional vessel enters an ecosystem, should we call it the smart fairway, where the intelligence is embedded to the fairway surrounding the vessel, allowing then a low threshold, for example, for vessel owners to join such a service. Remote pilot communicates with the vessel and receives data from the vessel and from the smart fairway, the ecosystem, if you like, that surrounds the vessel. No pilot boat, no commuting of pilots, no accommodation for pilots, no dangerous climbing on board, no waiting times, resource efficiency. Sounds very attractive. So in order to understand how the working environment for the remote pilot should be established, we launched the project ISTLA, Intelligent Shipping Technology Test Laboratory. This is in the heart of low threshold, financially sustainable and definitely bulletproof safe solution for researching new ways of delivering information for humans in remote locations. ISTLA project is a collaboration work with Finnish Transport and Communications Agency, Finnish Transport Infrastructure Agency, Geostatical Agency, Meteorological Institute, and so forth, where we are collecting data from the fairway and collecting data in a simulated environment from remotely piloted, vessel, and then summoning this data into a user interface for the remote pilot, and thus forming a novel way of establishing sufficient situational awareness for a human that is not on site in a marine operation. So what did we do actually practically in the testing? To date, we have done 3 test cycles in ISTLA to better understand the information requirements of the remote pilot and demands for the fairway, vessel, and human performance. 2 academic published papers are already there, linked over there for your familiarization. And this picture elaborates a little bit of how we are in practice aiming to find out how the situational awareness working environment should actually be established. What is actually the information that the remote pilot needs to be aware of what is going on in the fairway around the subject vessel being remotely piloted? So what we did was we used the distribution of pilot visual observation through specific glasses that are able to withdraw eye movement data of the remote pilot. And then we analyzed the data and split the information in between different sources of information. This allowed us, for example, to better understand what kind of information the remote pilot is collecting when he or she is navigating and advising the vessel to navigate through a straight or curved fairway section. What kind of data is being collected when there is a meeting with another vessel? Is there a specific area of data with which considerable amount of time is used, for example? This is the type of information and data collection that we have been doing, and this project is still much ongoing. We are looking forward to launch the next test cycle before the Christmas. Another project, C4Value Fairway, which is a Business Finland funded project, is to blueprints towards digitalization, service innovation, and information flows in maritime transportation. Pretty self-explanatory, C4Value Fairway. This project is all about understanding the demands of the fairway infrastructure for the establishment of the shared situational awareness for the fairway users. C4Value Fairway project has established sensor stations in archipelagic area, as illustrated in the picture. And we are about to do a test piloting with a bulk carrier from ESL Shipping, LNG-powered new-built motor vessel Haga in the Helsinki fairway, highly likely before the Christmas time this year in this project, where the remote pilot situational awareness in this project is constructed with the data transmission from the vessel and fairway sensor stations, while the remote pilot station is located in Turku, approximately 160 kilometers away from the navigable water area where the actual vessel is navigating. And having said that, C4Value Fairway has received funding from Business Finland and is coordinated by DMEC Limited, and the link can be found there to familiarize more with the C4Value Fairway project. The collaboration with different universities, with different companies is definitely in the heart of what we do in Satakunta University of Applied Sciences, and also in the University of Turku, which is another research institution that I represent here today. Unfortunately, there was nobody available with a relatively short notice to attend this conference from the University of Turku, but I have taken the research context of and achievements of the University of Turku also into consideration while summoning this information and presentation for yourselves. So, having said this, the University of Turku and Satakunta University of Applied Sciences have roots deep in the domestic and international research cooperation. We believe firmly, or we actually know firmly, that there's a lot of work done in the past. We've done a lot. This goes without saying. We have achieved a lot of great things, but this is the believing part. We believe that there is even more ahead of us than what is past. This is our approach. So we are really keenly looking into more collaborative projects with like-minded partners, both domestically and internationally, to find ways of learning these novel ways of doing and meeting the old targets in maritime domain. So we wish to join hands with constructive and forward-looking collaboration in the field of autonomous maritime research. Thank you very much for your time. I didn't actually look at the time at all, so I believe I was quite fast. But still, here are the connections and the contacts from both Satakunta University of Applied Sciences and from the University of Turku. So please, should you have anything that you wish to discuss, all collaboration proposals are very welcome, and looking forward to work together with all of you and listen to the novel ideas that you undoubtedly have. Many thanks for your time, and greetings from Rauma, Finland. Thank you.
Thank you very much, Professor Lahtinen. I would like to thank you for your double report concerning both the university and your researches. And I would like, it's better, sorry. And I would also underline the practicability of your report in concerning technical research, and also the accents that you have made on the safety and on collaboration. Just continue on the topic that Misa, the director of the Maritime Safety Division, has already highlighted today. It's all very important for the community. So I thank you once again, but I would like to ask if the participants in the meeting have any comments or questions to Professor Lahtinen. Please be welcome if you have any specific comments or questions, please. No comments, questions, but you have already shared your contacts. I think that after the meeting, the participants can contact you if they will have further comments and maybe proposals on collaboration and on cooperation. Thank you very much again. And now I would like, thank you once again. Now I would like to give floor to Professor Etsuro Shimizu from Tokyo University of Marine Science and Technology. Professor Shimizu, the floor is yours, please.
Yes, thank you very much for your kind introduction. And I'd like to share my slides. Just a moment, please. Yeah, can you hear the slides?
Now, yes, thank you. Thank you.
Yeah, okay, I'll start my presentation. So firstly, I'd like to thank you very much for you that to invite this very interesting conference and forum. So that's my pleasure to make a presentation at this conference. Today, I'd like to introduce the recent development on the MAS in Japan. Yeah, contents of my presentation is as follows. So firstly, I would like to introduce our university and Tokyo University of Marine Science and Technology, and also I would like to introduce myself. I forgot time, sorry, later I'll say to do that. And next, I would like to introduce the aim to develop the maritime autonomous surface ships. I would like to share the basic knowledge of that, basic aim of that. And next, I would like to introduce some research and development projects on MAS in Japan. And finally, I'll give them my conclude remarks. So I'm a professor of this university and at Tokyo University of Marine Science and Technology, and my research topic target is basically in marine cybernetics, and so apply the control technologies to some systems, especially for my university is maritime marine science and technology. So I apply the control technology to not only the ships but also the underwater vehicle and so on. Anyway, yeah. First, I'd like to introduce our university. So Tokyo University of Marine Science and Technology was established in 2003 by merging the Tokyo University of Mercantile Marine, which university was established in 1875, and Tokyo University of Fisheries, which was established 1888. So originally, our university has over 100 years history. And price, and so we have the two campuses. One is the Senaga campus, and formerly known as the Tokyo University of Fisheries, and the other one is the Tokyo Echijima campus, is formerly known as the Tokyo University Mercantile Marine. Both campus is placed in just center of the Tokyo area, and here is the center and Tokyo Station, and distance from the Tokyo Station to the Sinaga campus is about 6 kilometers, and Echijima campus is about 2.5 kilometers, just center of the Tokyo areas. So, and we use some experiments at this Tokyo Bay area. So, and then Tokyo University and TUMSAT and Tokyo University of Marine Science and Technology has one graduate school and one graduate school and 3 undergraduate school. And School of Marine Sciences, Marine Life and Science is engaged in education and research on natural life and social sciences related to the ocean. So, basically, originally the fisheries. And next one, I belong to this school, and School of Marine Technology is engaged in education and research on engineering related to the marine and maritime field, including ship officers and engineers. So later I'll explain again that about 30% of students will become the ship officer and ship officer and engineers. And yes. And final one is the School of Marine Resource and Environment. That school was established in 2017, so only 4 years. That's a new department, a new school for that. So this school is engaged on the use and development and the conservation of oceans. And next, I would like to explain our school and the School of Marine Technology. As told before, the School of Marine Technology is formerly known as the Tokyo University of Mercantile Marine. Is a large academic institution in Japan in the maritime field, engineering and logistic field. As told before, and 30% of students will become ship officers and engineers, especially for the international voyages. So maybe you know that graduate students will work at the NYK line and Mitsui SOK line and so on. And so, we, especially in our school, and give the education and training to become the ship officers and navigators. So we have these facilities. So, and just only few these pictures, and this is a training and research ship named Shinyomaru, and then these ships cruises sometimes to the Mariana Trench and so on. And this, and the second one is name is Shiojimaru, is especially used for the control system or something like that. And this is a just new one, and delivered from the shipyard in last month. So just new one. So I never won't get on this boat, ships. Sorry that. And final one is a pure electric boat. So generally, I use a lease boat to carry out my research, because a small boat is easy to operate that. And also, not only the vessel, but also that we have the onshore facilities like this, and these facilities test bed for the remote control center for the maritime autonomous surface ships. So you can see there are a lot of displays, and displays show the exist and radar map and camera movie and something like that. And also display the weather conditions. So we researched about we check the required knowledge to become the remote operator and so on. And also we tested the transmitting speed and resolution and something like that to use communication equipment. Yeah, and so next I would like to explain aim to develop the maritime autonomous surface ships. So I think that almost all the definition is the same as a country. So although there are some difference in depending on the country, but the purpose of research and development are the following: improvement of safety and operation. So this means that, as you know, that, for example, an automobile, an automatic brake system for the automobile were equipped and widely equipped on the actual cars, and some report from the insurance company told that the number of accidents was decreased by the automatic brake system. So, and such kind of an automatic control system is effective to decrease the number of accidents. So, such kind of similar technology is required to and useful for the ship side. So, of course, as you know, that we have a lot of accidents in the maritime field. So, in order to decrease the number of accidents, such kind of automatic technology is useful for that. And second and third one is almost similar. That so, as you know, that in Japanese we call the seafarer work is a 3K and 3K job, and so similar meaning in English is a 3D job, meaning that dull, dirty, and dangerous work. So number of seafarers is decreased in Japan. Maybe another country has the same problems. So in order to cover the number of seafarers, so we need to such kind of automatic technologies to support the human operator. And reduction in environmental impact and operational environmental impacts is not directly connected to the autonomous surface ships, but if the human not on the boat, on board the vessels, then the operational time is maybe neglected for that from the human aspects, a human point of view. That so operational time is extending is no problem for that. So and if speed of the ship is decreased, the energy consumption is also dramatically decreased. So in order to such kind of realize such kind of situation, so we will be able to use the autonomous surface ship technologies. And if the number and second and last and final second one is reduction of the operating cost is meaning that you can easily understand that if the ships on board and no seafarers on board, then we can decrease the cost. We can cut the seafarers' cost. But so maybe we need a more budget to equip the autonomous ship technologies to the boat, and so we need to consider about that. So future problems are. And final one is just target for just only for the researchers. So technical interest of engineering. So and as you know that autonomous field is automatic driving system is widely researched, actively researched for that. So such kind of technology and engineering considering about that, such kind of technology would like to install not only the car field, automobile field, but also the ship field. So basically, such kind of technical interests of that. So I think that almost the same as other countries. So next, I'd like to introduce the research and development project on math in Japan. So, so in order to realize the math, as you know that, these following functions were required. Autonomous ships. So this meaning that the ship can maneuver by herself, except without any perturbation and by the humans. So I mean that the automatic collision avoiding maneuver and something like that. And on this hand, so ship equips ships get on some passengers and souvenirs and something. So in order to monitor that, so we need a control center on the shore side. So and especially in Japan, so ship, not ship, and train has an automatic system. Almost all ships, the train has a automatic control system, but still human monitor is required on the train system. So similar kind of system is also required on the ship field. So we need a control system, a control center for that. And in order to connect the autonomous ship and the control center, we need a communication system, especially for the wireless communication system, including the satellite communication. And as you know, that satellite communication system is speed of the satellite communication system is a little bit too slow to transmit the movie and visual image, so that maybe in short side is some 4G communication system is effective for that. So we need to select such kind of communication system, depends on the situation, but also not only such kind of things, but also we need to take into account of what kind of information is required for that, for the control center and the remote operator for that. So we need to check and such kind of things. So so all these required function is almost same, and almost all projects requires for that. So next, I'd like to explain introduce some projects. So this is one company in Japan, Marine United, and developed a small autonomous craft and named because. So I'll show movie on. I found this movie on the website of the JMU that you can find this by yourself, and you check this website. So this is only for the written in the Japanese. So I would like to try to translate this word. So this is the one for the you say the autonomous boat, and displays autonomous bathing and unbathing that. This is a movie on the autonomous bathing. So this is a remote control center, and then remote operator check the monitor that and moving then this way and like this, and using this is a camera movie on the equipped on a boat. And very, so they say that and smooth bathing that like this. And later this ship unbathing from the pier. Yeah, this is a movie for the unbathings. And sorry, I skipped sorry, time is limited, so I like to skip the movie for that. So this is a collision avoiding maneuver, autonomous collision avoiding maneuver for that. So they detect the obstacle by using a LiDAR sensors. So, and automatically avoiding the collisions. They have already tested this kind of and test at the actual field. Yes. And sorry, and the next one, I would like to move to the next. So this is another example of the JMU system that. So this ship is the name is Kaisho Maru, it operated at the Kanmon Strait in the Kyushu area in Japan. Yeah, size of the vessel is about over 100 meters, and to realize fully automated berthing, leaving and mooring, and discharging work of the dredge sand from the vessel. So this vessel has been operated from the since April 2004. So already almost about 20 years operated in actual sea. So and then this is the unberthing station, a living station, and so this is a circle to hold the hull of the vessel. So you can difficult to understand that this is only for the moving from the land side, but I interviewed to the ship officers on this vessel. So they said that, so basically no problem to operation. Automatic operation is no problem to that. Only once or twice a year is misberthing of that. So that means so no accident, but so take over the maneuvering process by the ship officers on board, who on board. But so based on that such kind of situation is a reason is wind or strong current and so on. But so basically no problem to work with that. So now I am asking the JMU person to analyze such kind of result and announce to the person to show that. Yeah, sorry. Yeah, that's one. So, and yeah. Next, I'd like to introduce a new project started in 2020. Yeah. So, and Nippon Foundation and one of the founding organization in Japan and has assembled a decision to they funded to the 5 consortia to carry out the unmanned operation in an actual vessel. So, and these are 5 consortia. So later to verify the unmanned operation. Of course, as you know, that in regulatory point of view, that not allowed to the unmanned operation. So in current test is carrying out the peoples on board. And the system is just only tested to develop the unmanned operation system. So unfortunately we don't have the movie for the lead project, but so today I only introduce the size of the vessel and price of the experiments. So an Mississippi building and project is carried out from the Kanagawa Prefecture to the Kyushu area is over 100,000 distance from the Kanagawa Prefecture to the Kyushu area is over 100 kilometers. So they use this and ferry in size is over 200 meters. And the system on board is like this. And 2 thrusters, 2 bow thrusters, and 2 stern thrusters, and CP propulsion system. And they equip some autonomous system developed by the Mitsubishi company that. And so please, if interested in this project and this boat, and you can find more information Class NK technical journal of this year. And Next one is a bit of a small project, a small size of vessel. So it's about 20 meters length of that. So this is a sightseeing boat operated at the Yokosuka in Kanagawa Prefecture in close to the Tokyo area. So and then this operational area in here, and here is a Yokosuka in maybe in you know that base in U.S. Navy is placed in this place. And distance from the land side and island is about 1 nautical mile and 1.7 kilometers. And this is Sarushima is a unmanned, no human island. So just only for the sightseeing place. So they and Marubeni project would like to develop the unmanned system for this small passenger boat. So I heard from the Marubeni person, maybe at the end of this month, they have already tested on automatic berthing for that. And then, so I have asked to them to develop some movies and promotion, develop a promotion movie to do that. And so this is a big project and operated by the Japan Marine Science and a group company of the NYK Lines. So they have already developed a remote control set and a fleet control. They call them fleet operation center at the Chiba area. And this is a picture of the remote fleet operation center. And the demonstration trial will be carried out from the Tokyo Bay to the Ise Bay close to the Nagoya area. They use a 749 gross tonnage container ships to carry out this operation there. And so, and then MITS SOK line carry out, they carry out unmanned test, to develop the unmanned maritime autonomous system testing by using the lead tube ships. One is a cow ferry named Shiretoko. Size is almost 200, length of the vessel is 200 meters, and the other one is Mikage, in length is less than 100, almost 100 meters. So they can also find this kind of more precise information from the classified technical journal of this year. So, and so February of this year, they announced that automatic berthing using Shiretoko is successfully conducted by using their system. That maybe you can find some movies on the YouTube website. And final one is a little bit different size of the vessel. This is a amphibious vehicle and it's operated at the lake at the Gunma Prefecture. So sorry, I don't have the information about that, about this project. So I couldn't find out about that. Yeah, anyway. So my project and my research topics are that. So our university and my research also carried out a remote control system at the Tokyo Bay and Sumida River. And so my target is a small boat because a large vessel has been already carried out many companies in Japan. So I use a small boat, especially in Japan and Tokyo area. We have a lot of small canals and a small river that can operate the vessels. So we use that. We would like to develop some waterborne and transportation system. So we develop such kind of system for that. So, and then this is a movie for that. And sorry, and left-hand side is a camera equipped on a ship. And the right-hand side is transmitted movie from the vessel, boat to the onshore operation center, remote operation center in our campus. So, a student on my laboratory, they operated at this point, this small vessel, a boat from the land station by only using the camera information. And also in our topics is not only the technical side, but also the regulatory issues. So as told before that our university and almost about 30% of the students will become the ship officer and navigators. So we would like to take into account not only the technical point of view, but also operational side and human and seafarer viewpoints. So we would like, my research topic is including such kind of regulatory issues that. So that's the reason why we take into account such kind of point of view that, for example, as you know, that COROLEG defines how to maneuver the ships, how to avoid the accidents. So especially as many persons told that, it's a look at and define the COROLEG Rule 5 like this. So look at has been carried out by not only the site but also the hearing and also other available means. So we have to equip this on board vessel, and not only the camera, but also that we need to hearing system, microphone or something like that, so to recognize sound information that. But basically, almost all research take into focused on the camera vision and LiDAR system or something like that. So we announcing about that. We need to equip the microphone system and speaker system on that. And also, we also check the COROLEG Rule 3. So the Rule 3 defined that kind of vessels and the situation of the operational situation of the vessels, that power-driven vessel and sailing vessel using fishing and seaplane, and vessel not under command, and vessel restricting her ability to maneuver that. So as you know that, and how to avoid the accident, how to maneuver the vessels. So they're different, depends on the situation of the vessel, operational situation of the vessels of that. So as you know that, for example, AI system can detect the boat. My current system not only detects just only boat, but also some type of vessels, so container ship and tanker or cargo or something like that. Yeah, basically, and current AI system can detect the type of vessel, but in order to follow the COROLEG Rule 3, we need to detect not only the type of vessel, but also the situation of the operational situation of the vessels, especially vessel in engaging fishing or something and under command or something like that. Something like that. So such kind of detection is very important in the actual situation of that. So we would like to develop. So unfortunately, I cannot find a solution for that problem. So, but we need to find a solution to carry out, to realize this kind of problem that. And okay, so now I would like to conclude my talk. So in this presentation, I have introduced some research and development project on Mars in Japan. So, and some of parts of the technologies have already realized installed in actual vessel. For example, in a heading control system and or target course tracking control system is a required control system to realize autonomous surface ships. But that kind of control system already used almost all ships in current almost ships. So, but on the other hand, so total system, I mean that to carry out all operation required in ship navigation. So in that meaning for the berthing and berthing and loading, unloading and something and bunkering or something like that. So not a lot of operation still we don't have the solution for that. So that's from the engineering point of view and researcher point of view, that's lucky for us because we have a lot of problems. We have to solve that. But to realize the mass, so we still have a lot of problem for that. And also, also we have to take into account the situation that, so now we try to develop the mass systems, but so if applied such kind of system, that technologies that to the actual field, so today is a conventional system, tomorrow is almost all ships become the equipped autonomous surface ship. Technology is impossible to do that. So we have to take into account the situation, the coexistence, mass and conventional ships for that. So we have to develop not only a technology, but also rule and regulatory issues to carry out the autonomous ships for that. And finally, I would like to emphasize that not only the technology side, but also human side. So mental workload and the competence of remote operators for mass should be discussed in the future, especially in the world. So collaboration is we think that the collaboration is international collaboration is very important to carry out this kind of topics. So this kind of today's forum is very interesting for me that to share the problem for the world. Yes, thank you very much. So that's all my presentation. So if you have any question or comments on my presentation, please contact me that by email or something like that. Thank you.
Thank you very much, Professor Shimizu. Probably somebody from our esteemed audience have comments or questions just now. Please be welcome. If you would like to have a chance to address comments to Professor Shimizu just now.
Hello, this is Janne Lahtinen from Satakunta University of Applied Sciences, Finland.
Please.
Can you hear me?
Yes. Thank you very much.
Very good. Thanks for the very, very interesting and innovative presentation, Professor Shimizu.
Thank you very much.
I would like to maybe raise, or I'm not sure what is the right word, maybe emphasize or raise this view that you had a very good and important view, I think, towards the fact that there is inevitably going to be a considerable amount of time where these highly developed vessels, be them whatever levels of autonomy, will coexist in the same environment with conventional vessels and with conventional decision makers. Now, and when the keel is laid today, the expected lifespan of a vessel is probably somewhere around 25 to 30 years. So we are talking about decades, inevitably not years, which makes this a very interesting discussion, especially when thinking about the regulatory framework and the question of who should bend in this way. Should we bend ourselves or should we bend the road? Meaning, how do you see, Professor Shimizu? You have a very interesting views. Can you share your views of how do you see it? Who has the primary responsibility to change the regulatory framework in so that it enables different ways of establishing actually situational awareness when, for example, we are talking about the lookout
Yeah.
It is generally already known that the situational awareness is constructed very differently when it is a mass vessel. And thus my question is, how far do you think that the same rules should actually apply?
Yeah, so basically, so thank you very much for your question, and so interesting question. So, but as you know, sorry for that, so we spend a lot of time to realize, especially for the collision avoidance maneuver. But in MSc already discussed about how to realize maritime motor surface technologies, especially in currently, and if the seafarers are on board, we can easily test such kind of technologies. So from my point of view, that my recommendation method is to just only as a maybe an additional support as we equip such kind of mass technology to as a additional support system for the seafarers. So and test again and again. And if maybe in the near future, seafarers directly use such kind of autonomous navigation system and to do that. So no conservation of that seafarers. So that's a process for that. But so in Japanese point of view that, so in order to test such kind of, in order to carry out such kind of test, so shipping, especially in shipping company, contribution from of the shipping company is very important. So in the Japanese situation is very lucky for us because the shipping company and for example, NYK Line and Mitsui SOK Line is interested in the development of this kind of technology. So we have discussed with such company, and also the Japanese government also interested in, would like to realize autonomous surface ship technology ships. So we have discussed with not only the company but also a government person who attend the IMO conference or something like that. So I think that such kind of discussion is very important to realize that. So, of course, as you know, that already spent 4 years discussion to focus, just to discuss about the regulatory scoping exercise. So we need you say that a decade, 25, maybe in 25 years or more, but we can use this kind of similar, we can use some part of the technology to decrease accidents for that. So, and if such kind of system is useful for that, then a lot of seafarers use that. So my point. So that's my opinion to realize that this kind of technology that.
Thank you very much for the answer, Professor Shimizu. Very interesting discussion. Looking really forward to continue this. I have a lot of follow-up questions to discuss this further, but we are limited with time, so very interesting. Thank you.
Yeah, keep in touch for that. Thank you very much.
Thank you very much,
Professor Shimizu. Yeah, sorry that. Yeah, thank you very much.
Thank you. Your report was really very informative and it gave birth to discussion. So the part related to Meguri project was very interesting, as well as your point on the regulations and your points on the common approaches. And thank you very much for providing very informative videos which provided very clear vision for everybody of the technology. So thank you very much again. And dear colleagues, thank you. Dear colleagues, dear participants, as convened, we came to a small pause, 10 minutes pause, so we can now have a little pause till 11 as convened. So we'll have 12 minutes. So we'll restart, we'll come back and we'll meet again in 12 minutes. Thank you very much. Thank you.
Located in Wuhan, central China, with 60 years of history, Wuhan University of Technology is one of the leading universities under the direct administration of the Ministry of Education, and one of the first universities entered the State 211 project. From inland waterway to land to water and river to sea transportation, the former Wuhan Transportation University developed into a comprehensive university for talents cultivation and science and technology development for the transportation industry. The former Wuhan Automotive Polytechnic University was the important base for the development of science and technology and talents cultivation for the automobile industry. On May 27, 2000, Wuhan University of Technology was merged by the authorization of the State Council from above 3 predecessors, which made great contributions to the establishment of New China's industrial system and the development of 3 major industrial sectors. With a total occupying land area of 267 hectares, WUT owns 4 modern libraries, a total collection of 3,295,300 books, more than 200,000 square meters of modern sports venues, and over 50,000 faculty and students. It has 25 academic schools and 96 undergraduate programs, 91 master's programs, and 31 doctoral programs, as well as 17 postdoctoral research stations. Since 2017, the university was listed in Times Higher Education World University Rankings, U.S. News Best Global Universities Rankings, Shanghai Jiaotong University's Academic Ranking of World Universities, and QS World University Rankings. In 2021, the university rose to 301 to 400 on the academic ranking of world universities and ranked 73rd in U.S. News Asia University Rankings. In 2021, 5 disciplines in WUT, including material science, chemistry, engineering science, computer science, and environmental science, are listed in top 1% in ESI Global Discipline Ranking. Among them, material science and chemistry rank the top 1,000. WUT has made rapid development by following the principle of take the student's cultivation as our essence, and take academic development as our priority, and the spirit of sound in morality, broad in learning, and pursuing excellence. The university focuses on the lofty ideal of building an excellent university to win a worldwide recognition and admiration. Adhering to the strategy of strengthening itself through talents, WUT boasts a large talent group. The number of academicians has increased from 0 to 11. Among them, 5 are members of Chinese Academy of Sciences and Chinese Academy of Engineering, and 7 are academicians from developed countries. A high-end talent team composed of specially invited experts and chief professors has been built. Adhering to the concept of technological innovation, efforts have been made to carry out original innovation and make breakthroughs in the core technology research. A large number of high-level scientific and technological achievements with originality and social influence have been yielded. A series of original results obtained in the cutting-edge science field from the intersection of material science and energy and life sciences have been published in the world's top academic journals and have been cited by more than 115,000 scientific researchers worldwide. More than 50 research groups in developed countries have followed up and studied these researches. In 2018, as national statistics showed, WUT ranked 17th in the total number of 3 national awards for scientific and technological achievements among all Chinese universities. WUT focuses on transferring scientific and technological achievements into social productivity. It has made great contributions in serving major projects. The transformation and upgrading of the 3 major industrial sectors, and the development of regional economy and society. A number of important innovations have been achieved in green building materials, new energy materials, electronic information materials, biological materials, and new marine materials. Major breakthroughs have been made in key technologies for the large-scale use of solid waste and domestic waste as alternative raw materials to produce high-performance cement. These advancements have promoted the transformation and upgrading of China's cement industry. Achievements in key technologies have been widely used in more than 150 major national projects such as large-span bridges, tunnels, high-speed rail, highways, and the Three Gorges Dam, etc., and made significant contributions to the development of China's building materials industry. In the preparation theory and technology of fiber grading sensing and smart sensing, industrial production and engineering applications, WUT has solved international technical problems and formed a complete intellectual property system. Scientific and technological achievements have been applied to major basic engineering and equipment fields such as chemical industry, metallurgy, railways, highways, ships, ports on a large scale. A number of important innovations have been achieved in the fields of green smart ships, water and land transportation safety, smart transportation, and smart shipping, etc. WUT proposed and established the navigation brain system of intelligent ship to promote China's ship driving active safety technology and equipment innovation. The design and construction of the first direct river-to-sea demonstration ship, Han Hai No. 1, has opened the 1,000 boxes era of the Yangtze River inland shipping. In the areas of automobile lightweight, electrification, intelligence, and networking, WUT has broken through a series of core technologies and promoted the transformation and upgrading of the automobile industry. One of China's first 2 fuel cell cars, Qutian No. 1, was developed by WUT. The worldwide difficulty in high-performance component near-net molding manufacturing technology has also been overcome, which has realized the mass production of high-precision core structural parts in automobiles. High-speed railways, aero engines, have been widely used in Fortune 500 companies such as China Dongfeng, FAW, Toyota, GM, and CRRC, etc. In the Yangtze River Economic Belt, Guangdong, Hong Kong, Macau Greater Bay Area, Bohai Rim Economic Circle, and other regions, WUT has deployed more than 20 research institutes to promote and serve economic and social high-quality development. Awards in major competitions. In the 2018
Thank you. So shall we restart? It's a pleasure for me to give floor to Mr. Jin Kim of the Korean Institute of Ships and Ocean Engineering. The floor is yours, Mr. Kim, please.
Thank you. Okay, thank you, Chairman. Good afternoon in Europe and good evening in Asia. Today, I will introduce the recent Korea Autonomous Surface Ship Project and validation plan for an autonomous ship. My name is Jin Kim. I'm the head of this new Korean R&D project for maritime autonomous surface ship. This is a brief outline of the Korea Autonomous Surface Ship project. It is funded by Korean government and also participating private companies. The project period is 6 years, starting from last year. The goals are development of key technologies of autonomous ship and making a basement for commercialization of the developed systems through phase tests and validations. We defined 4 core technologies, such as intelligent navigation system and engine and machinery automation system, and especially sea test bed and validation technologies. And finally, operational technology and its standardization. We are targeting IMO level 3 in autonomy degree for ocean going and level 2 for coastal operation with real commercial ships. Let me show the members of the CAS consortium. CRISO, my institute, and Korean Register, KR, take charge in project management. Korean shipbuilding companies and shipping companies and small IT ventures and many Korean marine equipment companies, institutes, and also universities are participating in this project. In particular, Lloyd Register in UK also joined this project for the development of validation procedures. This chart shows the composition and development period of sub-project for each core technologies. The project consists of 4 core technologies and 13 sub-projects. We'll build a small test ship to validate all the developed digital systems. We also build a CAS shore control center, and it will be operated from next year. Finally, in the final 2 years, the developed autonomous technologies are equipped on the real commercial ship and validate with reliable test procedures. Let me talk about each core technologies. At the first core technology is the autonomous navigation system, which developed the autonomous navigation system that enables IMO level 3 autonomous degree in ocean-going operation. The core technology 1 consists of 3 sub-projects. At first, we'll develop the integrated platform and digital bridge for navigation and engine room control. Navigation awareness and collision avoidance develops a system to detect other ships and obstacles and provides situation information. And the final intelligent navigation system can make a navigation plan and collision avoidance support system considering ocean and coastal environments. The second core technology is the autonomous engine system, which enables IMO level 3 autonomous degree in all areas of engine and machinery operation, including port. The first sub-project develops the condition monitoring and intelligent fault diagnosis system. The second sub-project develops a system that provides an integrated simulation of all energy systems on ship, which can check compliance with environmental regulations. The core technology 3 established the infrastructure and developed the related technologies to verify the performance of advanced sensors, automated and intelligent systems, and all the developed technologies through the core technologies 1 through 2. It consists of 5 sub-projects, which includes we'll build a shore control center for autonomous ship and 24-meter class small test ship, and develops validation procedures for mass operation, and also develops remote control system on shore side, and also digital communication system for ship to shore and also ship to ship. And finally, cyber security systems are included in these core technologies. The fourth core technology is autonomous ship operation techniques in a viewpoint of shipping companies and standardization of mass technologies. Autonomous damage control system develops incident response system in case of fire and flooding. And also we developed the port linked decision support system and each platform. And finally, we suggest international standardization for mass technologies such as detailed autonomous degree and testing and validation procedures. In order to manage it and also help the development of 4 core technologies and 13 sub-projects, CAS project office is organized. This office consists of project head and vice head and staffs. In general, project head manages the sub-project funded by the Ministry of Trade, Industry and Energy, and the vice project head manages the sub-projects of Ministry of Oceans and Fisheries. We'll operate civilian commission for important decision making and advice. We are considering 3-phased validation steps, including simulation and next small test ship, and finally actual commercial ship test. In terms of validation for mass digital system, no appropriate procedures exist so far in the world. For the commercialization of mass, I think there could be 2 different types of challenges. The one is about how effectively to integrate all digital functions and verify them under some appropriate test bed and infrastructures. The other could be about how to get an accreditation or approval for commercial operations in safety and security points at least. I think that is the reason why validation of mass digital system is important. Mass control center will be constructed at Gonul district in Green Kala of Ulsan City. Ulsan City is located at southeastern shore side in Korean Peninsula. Nearby, there are Hyundai Heavy Industry and Hyundai Mipo Shipbuilding Yards. The right bottom photo shows a bird's eye view of mass control center, which is a radar dome on the top. The right above photo shows a range of radar covering area, and small 24-meter test ship will be operated in green-colored regions. The design of a mass control center was started at the end of last year. Groundbreaking ceremony was last month, this year. So this mass control center will be ready for operation in the middle of next year. The first step of validation is simulation-based test bed for autonomous ship. We named it as STAS. A real situation in the right side photo will be simulated in STAS system. We'll simulate a test ship with virtual other ships, virtual obstacles under the virtual ocean environment. The key technology for STAS would be, we call it VDGS, which is Virtual Data Generation System, will be developed, including marine obstacles, marine weather environment, and scenarios for testing. The STAS system will be equipped at Mass Control Center. The next step is testing a real ship at real ocean environment. The real ship and ocean environment replace virtual conditions of simulation-based system. Two real ships, such as a 24-meter class small test ship and actual commercial ship, this ship provided by participating shipping company will be tested in this project. We can operate the test in both or mixed generated virtual obstacles and also real obstacles. Mass Control Center will have a digital twin bridge and big data platform and communicate with the shipboard digital bridge. We'll develop the test scenarios and procedures to validate the intelligent navigation system and engine automation system, including cybersecurity. This shows a small test ship. We'll build this small test ship. The ship's main particulars are shown here. Test ship will be launched at the end of this year. Situation awareness system with sensors and digital bridge with autonomous navigation system will be equipped on this test ship. This slide shows the concept of system interface and data flow structures between an autonomous ship platform and mass control center. All data in a ship will be collected at the digital bridge, and also shore data will be collected at the digital twin bridge of mass control center. Ship-to-shore communication is performed through between digital bridge on ship and digital twin bridge on mass control center. We are adopting ISO 1984-7 and 1984-A for data standards. The Korean private companies will have R&D output such as engine automation, situation awareness, intelligent navigation, communication, cybersecurity, and etc. In terms of validation for mass digital systems, as I said earlier, no appropriate procedures exist so far. The commercial operation of mass in the future will strongly depend on how to get an accreditation or approval in safety and security point. This CAS project will develop the procedures for checking and validating all digital systems of mass. And we would like to cooperate with all other nations in order to make the international standard of mass verification, validation, and accreditations. The CAS project will help the participating Korean private companies to get the track records to make their business model themselves. This slide shows one methodology for validation of each digital systems on board. The CAS project cooperates with Lloyd Register for this digital twin-ready validations. The V model is adapted and will be followed from system goal to final validation. Now we are on the stage of component requirement and verification stage. At first, STAS for situation awareness, collision avoidance, and engine monitoring are now being evaluated through Lloyd Register digital compliance and risk assessment on this V model. STAS and the virtual data generation system will be approved for digital twin ready or approved in terms of both V model design approach and Lloyd Register digital compliance framework. Through digital twin systems, CAS project will validate each autonomous function reliably before onboarding. However, even though each digital systems are validated, we all still have a big challenge. It is how to approve or give a certification to a ship to sail in autonomous mode. We have to get a driver license to drive a car, but there is no appropriate license to sail in autonomous mode. Now is the time to discuss how to get an accreditation or approval for autonomous ship. We might need more detailed autonomous degree to evaluate mass. Now I'll finalize this is my summary. So Korean National R&D project for mass is launched in last year. Sea test bed, including a small test ship and a commercial ship, will be prepared for validation. Validation utilizes both the simulation-based and the real sea trial. All the data structures will be based on ISO standards so that CAS project could be contributed to future ISO revisions for autonomous navigation. Now is the time to discuss how to get an accreditation or approval for autonomous ships. Thank you for attention.
Thank you very much. And I would like to ask the attendants whether there are any questions or comments to our esteemed speaker. If there are no special comments for the moment, we can use the opportunity to contact Mr. Kim later on. And now I would like to thank him for sharing the very valuable expertise regarding the structuring of such important project, regarding testing facilities, infrastructure, regarding timing of the project, and regarding sharing the views about the necessity of verification and standardization of the project, regarding his views on the international standards in that view. Thank you very much again.
Okay, thank you very much.
Thank you. And now I would like to offer the floor to Mr. Odd Magne Nesvak of DNV from Norway for sharing his report and his views. Please, the floor is yours, Mr. Nesvak.
Yes, thanks. I will try. I get messaged here that someone else is sharing, so I cannot share the screen yet. Try again. So, could someone just confirm that it is the right screen that is now shared?
Not yet, not shared.
Let's wait and see if it comes. Still not there?
Not yet, sorry.
Then I will try one more time.
Yes, it starts.
Then no, I hope it should be up and going.
Excellent, excellent, thank you.
Okay, sorry for this. So, hi, and first of all, thanks for being invited to this event. My name is Odd Nesvåg, and I work in DNV at the Approval Center in Norway, where I, among other tasks, is involved in the service and rule development for smart, autonomous, and remotely operated vessels. Here, I will talk on some of the challenges linked to development of autonomous vessel in operation. And to set it in context, I will start with the role of class and the status of the rules and regulation for the assurance cases. And then further on the different focus area, and at the end, look a little bit on the market driver, the status, and the way forward. Just a moment. Just a little bit about the class role, which is important for the assurance cases. And the class societies has two main different roles. The first one is for classification society as a non-governmental organization who establish and maintain own rules for design and construction of the ships. And based on these rules, validates the construction is according to the rules, and based on compliance, issue the class certificate for the vessels. What is important in this case is that for the class rules, the class societies is the sole interpreter of the rules and can use professional judgment and analysis to accept equivalent solutions, or may also give deviation, normally then based on agreement with the owner and then listed in the second role. The second role is as a recognized organization. And in this, and here class verify compliance with the regulation by a flag state, and when authorized to do so by the flag administration. And then class may also issue statutory certificates according to authorization by the flag states. The difference here is that here class can also look into equivalent solution, but this has to be in agreement with the flag, and class is not allowed to accept any deviation from the statutory rules. So how does this relate to the rule status for unmanned and autonomous remote control vessels? Here, currently IMO flag states and classifications operation of an unmanned autonomous vessel. The existing rules is based on safe manning on board, and performance standard and rules for autonomous navigation system do not exist. There are also no clear requirement for remote operation center, and the communication links is also not established. And it is the flag that is responsible for safe manning of the vessel, and for autonomous vessel, the will necessary. So in the assurance case, how to handle this? Since the rules are not available, the approval must currently be based on a risk-based approach, aiming towards equivalent safety towards conventional manned vessels. IMO Circular 1455 is providing guidance on equivalent solution to ship and system design. And based on this, and in dialogue with the Norwegian Maritime Authority, DNV, back in 2018, developed the class guideline for autonomous operating vessels. which is based on the 1455 process, but also tailor-made towards autonomous and remote operations on the needed systems. In the DNV guideline for autonomous and one is the concept qualification to address the full scope and build on the vessel-specific concept of operation. And the other is the technology or system qualification to address how to assure performance of new technology where performance standards are not yet developed. NMA in Norway has also issued a circular on how to handle autonomous vessels who challenge the rules, and this is of course also based on the IMO circular 1455, and is aligned with and the DNV class guideline is aligned with the circular. And here there is a cooperation between flag and class such that the ensure in case in a good manner. So then more into the more details of the standard, which is also looking on 4 different focus areas. Of course, the overall acceptance criteria is that the vessel should be as safe as conventional ship operation. And the first area that the standard is mentioned is the navigational functions. Navigator, both with respect to object detection and classification, and navigation, which has to be colorway compliance. And this is the area where most technology development is needed. And it is an area that is still under development, and there is not yet a fully approved system for this. This relates to the ship machinery and system. And in this area, it is today highly automated, the vessels, as all of them more or less have periodically unattended machinery room. But also here, the rule and the operation of the vessel is highly dependent on competent of alarms and incident has in short time has access to the engine room to intervene and to take sufficient actions. So in going autonomous or unmanned, there has to be focus on the vessel design, focus on the robustness of the machinery and the system. Also the alert management system, which I will give one example of later on, has to be addressed, how to do and of course, there has to be a full new setup for how to do maintenance for these vessels, since a lot of the maintenance today is done during normal operations of the vessels. The third technical area is, of course, the communication. And of course, and the latency, the bandwidth and the latency of the communication has to be adapted to the situation that actually is certain awareness that is needed, and also to the requirements for the system that is submitted. And this has to be adapted for each and cybersecurity is of course coming in as a more bigger threat, as the vessel will be continuously connected, and there are no people on board who could take local action if there should be a security breach. And the last, but maybe not least area is the remote control centers, who is actually moving technical needs. That is one thing, of course, linked to the communication as well. But also the organizational setup here has to be looked upon because to get this commercial going, most of the setups are talking about handling fleet level and not only single vessels, and how to adapt this to information and ensure that you have a setup with sufficient both competence and sufficient manning to handle different incidents that may happen on one or several vessels at the same time. This is still a non-regulated area. Common for all of these functions, the technology today is there for normal functionality. That it's quite straightforward to set this up. The problem comes in the lower arrangement is about handling of failure and external events. Which for all the areas, when you are set up an unmanned vessel, the hand to build it and set it up, that everything is going as planned, is a huge task and will probably take a long time in operation to see all the possible hurdles that may occur. Huge, and there is ongoing research or development in all of these areas. Here I will just briefly go further into the COLREG compliant maneuvering with respect to testing, and also first mention something about the status for alert management on vessels. And starting with the alert management system, this is just an example coming from a research project in Norway, ROMAS, who as part of the project looked into the alarm given over 1 year of period of times for our coastal ferry. Has more than 126,000 alarms and events for this vessel. This is around 345 per day. And filtering this down, it was seen that a lot of these was actually events or notifications to the crew that actually need no actions. Events here, you come down to 28,000 alarms. And further looking into what kind of alarm that was and how these arrived, you could also see that a lot of these alarms was alarms coming due to the same. Say if you have an engine that is stopped for some reason, it normally may come 30 alarms, but it's due to the same reason that the engine stopped, and then there's a lot of different alarms coming. So filtering, when only there was a new audible alarm, then it actually went down to below 2,000 alarms. And then I think what is common in many of alarms arising coming from normal operation, like starting and stopping equipment, and this issue that that's also what filtering away. So taking away all, and also there was some of these alarms relates to testing and maintenance and was not really related to failure in any way. Taking away all this, which I think is very typical for a vessel, it came down to around 0.7 alarms per day you could relate to us and with respect to action need to be taken. And then is the question for unmanned machinery space and alert management. Is this system and the way they are set up, is that really the way to do it? And is it possible when you move alarm handling and handling to shore? And if you take into account that most of this is also planning to have fleet management, not single vessel alone, it's clearly stated that this is an area to actually need attention as well to have safe operation. It not necessarily means that all the events and all this should not come, but it has to be set up systems for how to route it and an organizational setup that is adapted to the operations. So this is just showing one of the complications and things to be thought of. The other area is how to do testing of the navigator. Today there is requirement for training of the navigator, there are training that they have the and so on. And when all this is going into the system, how to make it and how to be able to verify this kind of system. Here, in our opinion, it is this has to be based on simulator-based testing. And in this figure on the right side, you see a digital twin of the virtual world, where you have the digital twin of the vessel, and which the algorithm is going to be testing is running on. So you simulate the vessel and this one, and then you also have to simulate the operational environment, the weather condition, but also the operational area, coming with draft and constraints where the vessel is. And you have to the tester or the test management system, you have to be able to have a scenario manager where you can have control of the tests. And you also need to have a system that is able to evaluate the test going. And since to get a safe system and to get this to get this up and going, it has to be able to run bigger scenarios over time without having manual test needs all the time, so that you can run test cases and use machine learning to get the system up and verify the system to sufficient. Utilize historic IS data to adapt it to, say, the traffic that is in different areas, but this IS data should also be possible to manipulate such that you can interact and try out different scenarios when you. For this test scenario here, there are still, as far as we know, there are still no system that is really fully verified for full compliance to World Colweg, and there are still ongoing development to get sufficient test simulators in place. Towards autonomy. And of course, as always, it is the reduction of operational expenses, and where manning is a big part of it. But what we also see is that some of the first driver is doing this because of reduction of the carbon footprint and to move cargo transport from shore to sea. The short sea actors, that they are looking at the vessel as a part of their logistic. So they are looking for getting a interacted vessel, and to get this the cost down, they go into autonomous vessels as a possibility. What we also see is that outside of the autonomy, most of the owners, and it's going, there will be more or less, everyone will have centralized operations or possible for centralized surveillance of the vessels. This is, of course, is a big driver also then to take on task onshore for what's going on, and then build on autonomy or remote control and be a driver for this. The technology is almost ready, but it's a way forward. The connectivity, I think there is available money play and security and cost, but still not everywhere, meaning that depending on where you want to operate and the area, you will still need to plan for what you can achieve and what you cannot achieve. The automation level is available. For the short sea shipping, battery and electrical propulsion is normally used because taking away the manning, this system give maybe more, it's easier to operation for this kind of systems. And then you have the development of the advanced sensor for object detection and classification, who is ongoing and the one who are close or maybe already on the market. And the last is the possibility which needs to be a part of this, both for the system for situational awareness, but also for the navigator system, to build enough confidence over time and to learn from what is wrong. So in our view, it is still early days for autonomous vessels. And in DNV, back in 2014, we actually made this model Revolt. It was a small model powered on to doing research on. And this, in DNV, we are still doing research using this vessel, testing the anti-collision algorithms and sensor fusion, and combining data from different systems, IMRA and DITA, and so on. And also the use of simulator and the simulator testing, as I showed earlier, is part of the research going on. And I mentioned machine learning, and of course, the validation of machine learning system is also an area that we have to learn how to make sure that the machine learning happening is correct. And it's also not straightforward. There is research for this, for the strategic and research innovation, around 1% of our revenue. I think we use around 5% of revenue totally for research. When it comes to commercial use, there are actually still no cargo passenger vessel that is in full operation, as we know about, who has been fully unmanned and is operating commercial. So it's still early days. This is just a picture from some of the ongoing testing with the Revolt vessel. But what is ongoing is that there are several projects who utilize the alternative the design regime, as I presented in the beginning. But still some time ahead. And most of this vessel is smaller vessel, and also there are vessel that is for the short sea mostly. What we think is that when those vessels may drive on the research on the autonomous and remote systems, they will likely come to the bigger vessel long before those vessel is and be used as decision support system and could be system as shown here as auto docking and auto crossing and automatic mooring, but also open up for unmanned machinery space more than today, that are actually it may not be fully qualified crew on board, but still people who can do things, but with the competence sitting on shore or on the bridge, that it could maybe be periodically unmanned, meaning that you have a trustfully situal awareness system that could if there are more complicated situations coming. There are still a few challenges regarding how to qualify and verify this system, as I said, and there will go on. So the key factors for the involvement for this is still that firstly there has to be political interest and willingness to accept and also to put ahead research funding to go in this direction and make available test areas on this. As far as we see, this is then we also think there is still a need for cooperation among the different stakeholders in the project, from everything from the system suppliers and the academia, the class societies and the yards, the ship owners and operators, and also the maritime and coastal administrations. The insurance company has to be on and believe that what is coming out is safe enough for them to ensure. And overall, there has to be a holistic approach. And what we see still, at least when there are no rules there, that to go in the direction, you have to think from the beginning the concept of operation, and you have to think on the safety design and maintenance and operation philosophy. How you choose, what you choose will set the requirements to all the system. If you are choosing remote control, it set requirements to the connectivity, it's set to the bandwidth, to the latency, and so on. If you have less of connectivity and problem with the latency, you may have to put more on autonomy on the vessels and so on. So everything here is interconnected. Concepts is very important. And in this, there are challenges both with respect to on the technical side and system, the human factors, And as mentioned onshore, also the organizational aspects. How to set it up towards individual or fleet level, but also how to set up good system for maintenance and so on. And the need also to be agreement and up to the competence aspects and the requirement to people. So all in all, the technology is cheap, efficient, and safe. And so the whole industry has to look both on the technology, on the processes, referring here to the management systems, and to the competence. And in DNV, we are actually working on all of this. So we have the class guidelines and the rules for autonomous vessel for the technical side. And we are working with the standard for the ESM process together with the Norwegian authorities. And some standards and certification regimes for the remote control centers. So with this, I will thank you for listening in.
Thank you very much, Mr. Nesvik. I would like to ask the participants whether you have any comments or questions to Mr. Nesvik now.
Chairman, I have a question. Can I ask a question?
Yes, please.
Yes. Oh, okay, thank you. This is Xi Dechen from Wuhan University of Technology, China. Thank you for your excellent presentation. You just say the classification society are really playing an increasing importance role in driving the technology development. I want to ask you a question. What is the biggest obstacle to the practical use of autonomous ship technology? Technology or rules, economy or safety?
Sorry, Mr. Nesvik, can you close the screen sharing for we can see you?
No, sorry. So now I found it. I'm not so used to so. Yes, the biggest obstacles, I think it's hard to say only one, but at least if you look for as I mentioned, now there are mostly going on with smaller vessels and vessels with short travel distances. And of course, a lot of this is, now I'm talking about unmanned vessels, because that I didn't mention, but of course, and as long as you have people on board, there's a lot that can be done, I think. But if you move the people, and the goal is to say we have unmanned autonomous vessels, I think the maintenance and how to handle the failures in a way that you may get it safe, but you also to get this availability of the vessel up. And that means that there may be some, this is not on so much on the technology side, but this on how to design and make this fly in a way that you actually are able to operate. I think that is a way forward to come there. And that's the reason I think that this is starting with vessel who is most of the time at shore and easy to do maintenance and have time to, because they can move. And the last one, of course, the other issue that is more on the technology side is what I presented on the Colreg and to get system that are able to take into all situation in the same way as a human on board will do. It is not easy. And I think this has been addressed with autonomous car for many years, that this talk that it will soon come, but it is delayed because there as well, there are so many things that to be able to upfront make the algorithms able to handle it, it's a challenge. So I think those two is maybe the two biggest obstacles.
Okay, thank you very much.
Thank you very much, Mr. Nesvik. But I can't but only share the opinion of our colleague from Wuhan University as to thank you for sharing the opinion of the classification society and if not the classification community. Thank you very much.
Thanks.
Thank you. And now I would like to give the floor, or rather to cede my microphone to Mr. Pinsky, who, because we are just at the same table. And I ask you, Mr. Pinsky, to share your report, please.
Thank you very much. Good afternoon, good evening, dear colleagues. I'm asked to share the presentation, please. From the very beginning, yes, it's not a very beginning, but I'll try to jump to the very beginning. So, colleagues, first of all, I would like to say that the recent autonomous navigation developments, or A-navigation, as we name it currently to make it more short, are provided in Russia within the complex project. This one project is involving several major shipping companies of Russia, technology companies, university, Russian headquartered classification society, Russian Maritime Register of Shipping, Russian Maritime Administration, as well as related ministries. And the aim of this project is very practical. So we are not trying to prove feasibility of 100% unmanned vessel or something like this, maybe because we believe that it is feasible. We want to make A-navigation technologies available for customers, for shipping companies, because our strong belief that new technologies can mature only in hands of consumers, of customers. So idea behind this project, the strategic goal of this project is to make these technologies available for wide practical use by shipping companies starting from this year. So we have started this project in 2019 by the group of companies, as I said, with support of several ministries of Russia. And we made several steps, which I'll briefly describe. We have developed our own methodology. We have developed a technological set of solutions, which could be applicable, installed on any kind of ship, including retrofit ships. So we are not waiting for some absolutely new kind of vessels. We have developed national regulation for mass use. We made, and we are continuing, extensive trials of new technologies, of these new commercial products in real conditions, in real commercial civil operation on board several vessels. And this year, upon completion this trial project, we are starting the national experiment of A-navigation. Within this experiment, any shipping company can equip any vessel under the Russian flag with autonomous navigation systems and legally operate them in commercial conditions in civil operation. So a few words about methodology. Our methodology, which we name as Complete Functional Equivalence Principle, is pretty similar to what was explained by Mr. Nesvak from DNV, talking about equivalent solutions to the existing requirements. This principle means that independently to mode of control in automatic or remote mode or in traditional mode, the ship should fulfill all the functions which are currently prescribed to the human on board by the current international safety regulation. So we are not just looking for equivalent solutions, we are just making equivalence of each functions made by human on board in automatic or in remote mode. On the one hand, this guarantees that mass can coexist with conventional vessels, which was a critical point mentioned several times today, including opening remarks by Heike Degim. And the idea is very simple. If we follow the existing functions, the existing regulations, when you meet autonomous vessel, you can expect that everything which is done by this vessel is absolutely predictable. This autonomous vessel will behave as a traditional conventional vessel and even better, because human crew can violate the existing rules, the existing requirements, and the autonomous vessel will always strictly fulfill the existing regulation requirements. So this will make mass operation predictable and understandable, and will provide coexistence of autonomous and conventional vessels. At the same time, since we have the equivalent solution meeting the existing, the current international regulation, we don't need to change, we don't need to wait for changes in the safety regulation, so we can operate autonomous navigation following this complete functional equivalence principle within international regulation as is. As a ground for this approach, we took international and national regulation. First of all, STCW code, which is already pretty functional oriented. And we put as a functional requirements all competence requirements to the crew on board now. And here we had a great contribution by universities, because universities are training navigators. Universities are training seafarers, and universities just said what should be done in each particular case by automatic and remote control system to be equivalent to meet these competence requirements. For example, if currently crew on board should use compass, should control technical conditions of this device, should validate and integrate this data with other devices, etc. This is a requirement for us, which is fulfilled also by computer autonomous systems as well. If we need, for example, to use EGDIS or automated radar data, the same, this is requirement for us for autonomous navigation system as well. So this is pretty simple methodology to explain, but it was pretty difficult to implement. But eventually we can say that currently we have both technology and regulation, which is following this complete functional equivalence principle. From technology point of view, we just took and analyzed, reviewed these functional requirements for the, first of all, the existing technical solution. As Professor Jan Sinpin from Wuhan University of Technology explained, we already today have a lot of smart systems, and some of them are even mandatory to be installed, mandatory for installation for the existing merchant ships. For example, radar, automated information system, EGDIS or integrated navigation systems, etc. These are already mandatory systems for SOLAS compliant vessels. At the same time, we have already conventional technical systems. First of all, I'm talking about engine and engineering system as control for unattended machine rooms, ships. For ships with unattended machine rooms. In this case, we have a very high level of automation, and we just took this already existing remote control outside the vessel. Also, we have conventional motion control systems, dynamic positioning systems, automatic mooring systems, track following systems, which we also use to make, for example, equivalence of steering functions which are currently executed by human on board. The only difference that for these systems, in our case, the commands are sent not only by human, but also by computer system or by remote control station. Using this approach, we came to several gaps which to be covered by new technologies, by new systems. These are autonomous navigation system, optical surveillance systems, and remote control station. Autonomous navigation system, I'll try to switch my, yes. So autonomous navigation systems is actually equivalent of officer on board, integrating and synchronizing different navigational data from different sources. Here you may see the real video from a large ship working in automatic mode in heavy traffic area. So it, as you might see, it recognized several vessels with high risk of collision, or correctly with potential collision, definitely, and calculated maneuver to avoid it. So autonomous navigation systems integrates all the data which are currently available for the crew on board, including also optical data from optical surveillance systems. In accordance with the algorithm based on Colrex, it is calculating maneuvers to avoid collisions with other vessels and other hazards. And also it is working as a human interface, allowing for people either on board or in remote control station to interact with autonomous navigation system. So here you may see just an example of many trials made during over the past year within this trial project. Optical surveillance and analysis system. It is an equivalent of human eyes. Again, technically, we can avoid optical data for autonomous vessel, but since we are following the complete functional equivalence principle, and all conventions say that we need to provide visual observation, we are using optical systems to automatically recognize, identify objects around the vessel, and send it both in machine reading form to autonomous navigation system and as a picture, video, image to the human interfaces. Again, we believe that it is at least the same level of situational awareness in comparison with the human eyes, but definitely optical surveillance system has many advantages like 360 degrees permanent observation, ability to work at the same time in visual and infrared range, and etc., etc. Moreover, we can use it with augmented reality. We can use even completely virtual model, which is dramatically extend abilities for situational awareness. The same, we have internal video systems to control room spaces and equipment with video systems. Then we have also a remote control station. Here you might see again a video of one of trials in real commercial operation on one of merchant vessels. Here you might see the remote control station, which is equivalent of the bridge, but outside the vessel. So we have the same interfaces which are available on the bridge. We have the same visual observation, even better, which is available on the bridge. We have opportunity to communicate video radio equipment, loudspeakers, to send commands to signal systems, signaling systems. And all this equipment is combined in some kind of symbiotic way of use. So dependent on situation or dependent on autonomous level, we can use different ship controls during the voyage to make the most adequate way of control for the specific situation. For example, it could be fully automatic mode in high seas in standard situation. It could be remote operator, for example, in non-standard situation, or in some limited cases, it could be human on board. But in general, I would share approach, I would share opinion by Mr. Nespak that independently to autonomy level, we believe that for many years we will see people on board as technical maintenance teams. We name it emergency teams. So these people will not navigate, will not control the vessel in standard situations, but it will be this team will be required in case of emergency cases, in case of some technical failures or absolutely non-standard situation, or for example, search and rescue situation mission, so something like this. In parallel with technologies development, we have developed also national regulation, because shipping company says that we need to have clear guidance, a clear allowance by the Maritime Administration to use autonomous vessels in civil operation. So you know that as it was told today, the International Maritime Organization made several steps. In 2019, IMO approved interim guideline for mass trials, which is a document open opportunity for trial operation of autonomous vessels. It is recommendation, but it's already some kind of guideline, international guidelines. Also, this year, 3 major IMO committees completed regulatory scoping exercise and came to the more or less the same conclusion that mostly autonomous vessels could be accommodated in the existing regulatory, but there are some common potential gaps which should be regulated specifically for autonomous vessels. First of all, this meaning of terms master and crew for pure unmanned vessels, state of remote operator and remote control station and requirements to them, provision requiring actions by personnel, certificates and other documents. So in Russia, we have responded to these international, I would say, regulation, to this approach by the IMO with national legislation. First of all, last year, in December last year, Russian government as a state flag administration approved regulations on the national experiment. I already mentioned that within this national experiment, it is possible to legally operate autonomous vessel under the Russian flag. It is considered as an extensive trial operation, nationwide trial operation in real commercial conditions and real civil operation. These regulations implies development and approval of COLREX interpretation by the Federal Agency of Maritime and River Transport of Russia. So following our complete functional equivalent principle, we say that all these vessels should fulfill all the requirements of international regulation as is, and COLREX is a definitely key convention, as it was already several times mentioned today. Also, this regulation allows to decrease number of crew on board for autonomous vessels. And also currently, we are at the final stage of the approval after more than 1 year of approvals by different legal authorities. We came currently to the Parliament with a federal law on changes to Merchant Shipping Code. This is a major document for national regulation in maritime industry in Russia, and to other laws, interpreting these potential gaps which are highlighted by the regulatory scoping exercises by the IMO. So following a complete functional equivalent principle, we just answering how every this gap equivalently will be implemented in the autonomous vessels. So these documents are probably the first national regulation of autonomous navigation in the world, and we are ready to share these documents with all the interested parties. Also, as I said, in January this year, Federal Agency for Maritime and River Transport issued recommendations on application of COLREX by autonomous ships. Actually, this is the mathematically very clear algorithm based on scenarios and algorithm explanation interpretation of COLREX as is. Again, universities made very great contributions since, as I said, universities train people how to follow COLREX. They had the opportunity to explain to our programming engineers and to computer guys in mathematical way what is behind each of provisions of COLREX. And these recommendations are approved by Russian Maritime Administration. We are ready to share this as well with all interested parties, and I believe that probably this collision avoidance algorithm or correctly interpretations of COLREX for autonomous ships could be one of the topic for international cooperation, for example, for joint international laboratory, because currently we are talking about Russian Maritime Administration interpretation, but definitely together we can work and we can provide international harmonized interpretation of COLREX, which would be acceptable for any countries worldwide. And it would not require, for example, any changes in COLREX possibly. Next, as I said, we have extensive trials in real conditions. So after risk assessment, after the development of software and etc., last year we made preliminary test on systems in simulation environment and installed it on board on several commercial vessels in real operation. And these trials are made again in very simple manner. During normal commercial voyages, upon decision of master on board, autonomous mode is activated and vessel is working in automatic and remote mode. Mostly last months from April, we are working mostly in pure automatic mode. So remote control is more or less okay. Starting from February, we don't see any big issues with the remote control mode. And currently we are mostly working with automatic mode. So in December last year, we've got approval in principle by Russian Maritime Register of Shipping. So we have for these commercial products approval for by the Classification Society. Currently, we are completing this trial operation with demonstrational voyages, and hopefully very soon we will get federal law as a final document required for national regulation, and we will start national experiment on A navigation. So again, here you may see just one of examples of how this trial operation is conducted within the trial project. Again, normal light ship, again, normal commercial voyage, just starting, turning on autonomous mode. And here you may see that automatic autonomous navigation system in automatic mode is following vessel on the road, find dangerous objects and calculate maneuvers to avoid this. So, talking about the national experiment. As I said, currently we are starting already to implementation of autonomous systems for civil operation on board on several vessels. Here you may see some of the first vessels to be equipped next year, this and next year, and next year these vessels will obtain already official category, official class of autonomy by the Russian Maritime Register of Shipping. I would like to say a few words about the left side. This is a railway ferry, which will work between St. Petersburg and Kaliningrad. It is about 1,000 miles road. It is interesting that here we will we plan to integrate autonomous navigation with vessel traffic management systems via e-navigation services. As Professor Lahtinen said, it is very important to make not only autonomous vessel, but also infrastructure, safe infrastructure for autonomous navigation. And we believe that e-navigation and vessel traffic systems upgraded with e-navigation services should be natural infrastructure for autonomous navigation. So during next 2 years, we plan to integrate vessel traffic management systems of St. Petersburg and Kaliningrad with autonomous navigation systems, and we will try to understand and to present how such infrastructure, future safe infrastructure for autonomous navigation could work. Also, what I'd like to say, and here I would like also to support opinion by Mr. Nesvak, talking to many shipping companies, not only in Russia, but already with some shipping companies outside Russia discussing implementation of autonomous vessels, we came to the conclusion that actually we will see a very fragmented, I would say, process of implementation of a navigation system. Depending on economic model, depending on expectation by ship owners, it seems that we will see very fragmented implementation. For example, in some cases, for example, passenger shipping companies are interested in remote control. They are not too much interested in automation, but they would like to increase control by shipping company. Everybody remember Costa Concordia, and passenger shipping companies would like to have remote control as an additional tool for control by shipping companies. Otherwise, some companies say that no, we don't need remote control at all. We don't want to spend money on communications, on remote crew. We would like to have only automatic collision system, for example, to make a less number of people on board, to make it more comfortable for navigators. Some say that, for example, we need mooring system, or some say it's too expensive for us. We can pay cheaper for people in port to make mooring operation, and etc. So I would say that what we see now is that we put on the table comprehensive set of technologies, of solutions, but shipping companies will select only some parts of these solutions and implement following our economic benefits, following our view. Idea, as you remember, was to bring the technologies to consumers' hands. And now we will see how consumers will work with these autonomous navigation technologies in reality. And also what I'd like to say is that it is very promising, in my opinion, an interesting initiative by Russian University of Transport to cooperate with the shipping companies in the development of training programs. Starting from the next year, Russian University of Transport and some other universities in Russia will start to develop and to implement training programs for specialists in autonomous navigation. But today, nobody knows how we should work I'm not talking even how we should train. And idea, this initiative of Russian University of Transport is to use teachers of universities as remote operators for the commercial vessels. So we are coming to the agreement with the shipping companies who will operate these first autonomous vessels to agree that remote operators will be teachers of universities. So our teachers will get the unique practical experience and will convert this, transform this practical experience into the educational programs. And I think that such initiative could be also one of the topics for international cooperation, for example, within this international joint lab, because I believe it would be great to have opportunity for different universities from different countries to cooperate with different shipping companies to get this real practical experience, which is that definitely should be ground for further training and certification of remote crew, of remote operators. Here, I would like to stop my presentation. Thank you very much for your attention, and please stop the presentation, the screen sharing.
Thank you very much. Traditionally, I would like to ask the audience if there are any comments or questions just now, when we have the opportunity to ask those questions face to face. Please, are there any questions?
Good afternoon. Can I ask a question?
Please, come on.
Yes, so my name is Victor and I'm working for Aalto University. I'm a safety engineer by background. My question is, you have mentioned that you're using functional equivalence as a basis for rules development. But what sort of procedures or methods are you using in order to demonstrate equivalence in terms of safety and performance in safety? Thank you very much.
Well, actually, we are following the same procedure which was described by our colleagues by DNV. So we have a risk assessment, a detailed risk assessment conducted by Classification Society to confirm that this is an equivalent solution to meet the existing requirements. Last year, Russian Maritime Register of Shipping has developed rules for classification of maritime autonomous surface ships, as well as rules for cybersecurity. So based on these rules, we made actually this assessment. Also, what is less formal, but in my opinion, even more important, we have 3 shipping companies with typical normal masters and crew on board who are working currently in this trial operation and who provide feedback regarding their own opinion as the seafarers, as the navigators. Is it correct from their point of view or not? So we have, as I said, pretty formal assessment by Classification Society and less formal but very valuable input by shipping companies, by ship owners who are working on these vessels right now.
Thank you very much.
Thank you. Thank you. If there are no any other questions, I would like to thank you, Alexander, but I will not comment the details as I will be not impartial as we are the colleagues. So thank you very much, but I think it was important and very extensive report. And I would like to ask now the chairman, as the named chairman and the co-chairman of today's session to kindly sum up today's session, if it is possible, and to share their opinions on the results of today's session. Please, distinguished co-chairman, can you kindly share your opinions, please?
好的。今天呢，我们一天的会啊，一共到现在
Thank you. It's been 6.5 hours already since we began this meeting. It's a highly rich. It's highly enriched in the content. We listened to 7 keynote presentations focusing on intelligent autonomous vessels. We learned about the research already done in 6 countries. We also had perspectives from various sides, including the classification society, universities, and research institutes, as well as the industrial the industry and the regulators. So we looked at the issue from multiple sides. The conclusion is a very optimistic one, and we are going to work together to promote the research on the intelligent autonomous vessels to guarantee the reliability in the future. And also in terms of the function, performance, it's going to be exceeding human beings. And on the other hand, we are going to promote the future rules and guidelines introduced by various countries as well as IMO, so as to make sure the technology can be applied in reality. I have this feeling that our meeting today has brought to everyone engaged in the research on intelligent autonomous vessels great confidence that this study is going to be carried on with much more depth. So today, through this online platform of Zoom, we have reached over 1,100 to 1,200 audience. So our conference is generating a wide influence in the society. This is also beneficial for the further development of our cause. And taking this opportunity, I would like to thank all our speakers in the afternoon for your wonderful presentations and the efforts you've made in preparing these presentations. Thank you all very much. I would also like to thank my co-chair for the excellent job done. Thank you.
Thank you very much, dear Mr. Chairman. And I would like to ask Mr. Alexander Klimov, the co-chair of today's session, also to share his opinion. Please.
Thank you very much, dear co-chairman, dear participants, colleagues. It was a very fruitful and professional discussion today, and I'm very glad to have got the opportunity to attend the forum, and it was an excellent chance to share experience, ideas, views, opinions, and I can say that there are many commonly shared approaches that opens very good long-term prospects for collaboration and cooperation between the participants. I wish you fruitful work tomorrow, and thank you once again.
Thank you very much, Mr. Director. So thank you very much to all the participants, and I think that we can now declare our today's session closed. Thank you very much once again. Have a good evening or good night, depending on the time zone. Goodbye until tomorrow. Thank you very much once again.